Hello everybody, my name is Gustavo Rezende Silva and I will present the paper with the title Embedded Architecture Composed of Cognitive Agents and ROS for Programming Intelligent Robots. Here's a brief summary of what I'll be talking today. I will start with the introduction, then I will describe the Jason-ROS architecture, then I will detail the experiments performed in this work, I'll talk a little bit about the conclusions, and I will end up with the future works. Nowadays, there is an increase in the demand for intelligent robots. Intelligent robots require autonomous software that is capable of perceiving the environment, reasoning about what it knows, and then choosing how to act. We believe that multi-agent system is a good solution for this task, mainly because it addresses the issue of balancing reactivity and proactiveness. In special, we believe that agents based on the cognitive notions of belief, desire, and intention, the so-called BDI agents, solve this problem very well. In this work, we present an architecture composed of cognitive agents based on the notions of BDI and ROS, the Robot Operating System for Programming Intelligent Robots. We use JSON as BDI programming language since we believe it eases the process of programming complex behaviors. Also, the use of ROS allows that BDI agents are used in complex applications. In this work, we use a multi-agent system composed of UAVs as testbed to access the advantage of using BDI agents as a programming paradigm. The architecture proposed in this work can be summarized with this figure. Basically, it uses 4 ROS nodes: the agent node, the HwBridge node, the hardware controller node, and the communication node. The agent node is the cognitive part of the agent, the JSON program. The hardware controller node is the one that actually controls the hardware. It can be a real hardware or it can be a simulation. The HwBridge node serves as a bridge between the agent node and the hardware controller node. Basically, it translates the message from the agent node to the hardware controller node, in a way that the agent node doesn't need to know what the hardware controller node is. The communication node is used for the communication between agents running in different ROS masters. It can use any type of network interface and network protocols. The agent node communicates with the HwBridge node and the con node. To communicate with the HwBridge node, it uses 3 distinct topics. It subscribes to JSON perceptions to get new perceptions. It publishes to JSON actions to send new actions it wants to perform. It subscribes to JSON action status to receive the status of an action previously sent. And to communicate with the con node, it publishes to JSON send message to send new messages. And it subscribes to JSON receive message to get new messages. All these topics use a custom type of message that I will explain next. An important thing to highlight here is that the agent node doesn't have any information about the hardware. It is all abstract. The message types used by the agent node are the perception, which has a header with metadata, a string with the perception name, an array of string with the parameters, a field called update, which indicates if the perception should be updated or added in the belief base. The action type, which also has a header, a string with the action name, and an array of string with the parameters. The action status type, which has a header with metadata, a field called result, which indicates if the action was successfully executed or not, and ID, which is a unique identifier of an action that was previously sent. And finally, the message type, which has a header with metadata and a string with the actual data. In order to include all these functionalities into the agent, it was necessary to overload a JSON class called agarc. The methods that were overloaded are listed in this table. agarc uses Java, therefore it was necessary to use ROS Java to include ROS functionalities into Java. It's important to highlight that this is all transparent for a JSON programmer. The JSON programmer doesn't need to modify any code in Java, it only uses the modified agarc. This is an advantage of this method because it allows that a programmer that only has knowledge about JSON to program complex behaviors for robots. The HwBridge node communicates with the agent node and with the hardware controller node. To communicate with the agent node, it uses the same topics as I just described, but in opposite direction. When the agent node publishes to a topic, the HwBridge node subscribes to that topic. In order to communicate with the hardware controller node, it uses specific topics and services. These topics and services are configured via a configuration file called manifest. The HwBridge node is one of the main advantages of this proposal. It is a general-purpose node used to communicate with the hardware. For each different type of perception and action, a specific top or service is used to communicate with the hardware controller node. These topics and services are configured via two configuration files, the perception manifest and the action manifest. An example of a perception configured in a perception manifest can be seen here. The perception name goes between square brackets. The topic name used for this perception goes in the name field. The message type goes in the message type field. The message dependencies goes in the dependency fields. The arguments used goes in the args field. And buff stands for belief update functor, which can be either update or add. If it is update, the perception is updated in the belief base, or if it is add, it is added in the belief base. The resulting perception of this perception manifest can be seen here. It is pose, with 3 being x, 2 being y, and 0.3 being theta. An example of an action configured in an action manifest can be seen here. The name of the action goes between square brackets. In the method field, it goes either topic or service depending on each action. The name of the topic or service goes in the name field. The message type goes in the message type field. The dependencies of this message goes in the dependency fields. The name of the parameters goes in the params name. Here, the parameters can be concatenated. For example, twist has a field called linear, and linear has a field called x. So there can be several parameters concatenated. The params type field is used to indicate the type of each parameter. In this case, linear x, linear y, and linear z are all of the type float. If none is specified, it is supposed to be a string. The resulting action from this action manifest can be seen here. It is cmd val with 1.5 being linear x, 0 being linear y, and 0 being linear z. The hardware controller node is the one that actually controls the hardware. A lot of robots nowadays already have a ROS package for doing that. For example, if you want to use an UAV, you can use mav-ROS to command the UAV. If you want to use a wheeled robot, you can use ROS area for doing that. So basically, any ROS package can be used here. And if there is no ROS package available, you can implement one as you would normally do. In this figure, you can see the sequence diagram of the proposed architecture. When the agent node wants to perform an action, it sends an action to the HwBridge node, which translates the action using the action manifest. Then, it sends the translated action to the hardware controller node, which performs the action and then sends back an action status to the HwBridge node, which sends the action status back to the agent node. For the perception, the HwBridge node subscribes to the topics described in the perception manifest, and when it receives a perception from the hardware controller node, it translates the perception into the perception type and then sends it back to the agent node. The com node communicates with the agent node using the same topics as I previously described, but in the opposite direction. It subscribes to JSON message to get new message sent from the agent, and it publishes into JSON receive message to send new messages to the agent. The communication node enables agents running with different ROS masters to communicate with each other. It is left to the user to develop this node. It also has to decide which technology to use. The only requirement is that the message data field must comply with the JSON message specification. The JSON message specification can be seen here. The ID is the unique identifier for the message. The sender is the name of the agent sending the message. ETL force is the illocutionary force, for example, ask or tell. The receiver is the name of the agent receiving the message, and data is the information being sent. A multi-agent system composed of UAVs is going to be used as testbed for the proposed architecture. Two missions are going to be performed. One with a single UAV that's going to be used as test of concept, and another one with multiple UAVs that is going to be used to access the advantages of using BDI agents as a programming paradigm. The experiments are going to be executed as a hardware-in-the-loop simulation. The proposed architecture is going to be embedded in a Raspberry Pi 3. In a host PC, ArduPilot software-in-the-loop is going to be used as simulator. And MAVI-ROS is going to be used as hardware controller node to command ArduPilot. The single UAV mission consists in the UAV having to take off, fly to a predefined waypoint, return to home, and finally land. This experiment was successfully executed in a Raspberry Pi 3. With this, we are able to conclude that it's feasible to integrate JSON and ROS within an embedded device. After that, the agent node was replaced by one programmed with Python and the mission was repeated. CPU and memory usage were collected during the execution of both agents, the JSON agent and the Python agent. With that, we are able to conclude that JSON uses more computational resources than Python. In this specific case, 256% more CPU and 231% more memory. We also wanted to analyze the ease of programming behaviors with JSON. In our opinion, it's easier to program complex behaviors using JSON. But we collected some metrics to support that idea, such as the size of the programs, their number of lines, and their number of words. In this case, JSON had a smaller size and a smaller number of lines and number of words, which is an indicative of JSON being easier to program. However, the proposed architecture has a development overhead due to the manifests and setting up ROS Java. The next experiment consists in a more complex mission to better understand and evaluate the usage of JSON. It is a search and rescue mission, with one scout that has to fly around, look for victims. When he finds a victim, inform the rescuers about the victim's position, and then it lands. And two rescuers that has to take off, fly to the victim's position, drops the boy, and then land. Each agent is embedded in a distinct Raspberry Pi, and the simulation runs in a separate desktop computer. Once again, the JSON agents were replaced by a Python agent, and CPU and memory usage were collected during the execution of both agents. As expected, the JSON program consumed more computational resources than Python. In this specific use case, 231% more CPU and 230% more memory. In our opinion, it was undoubtedly easier to program the behavior logic using JSON, but again, we collected some metrics to support that idea, such as the size of the programs, the number of lines, and the number of words. And once again, JSON had a smaller number of lines, a smaller number of words, and a smaller size. Another disadvantage of Python is that it required multi-threading and locks, which made the programming more complex. With this, we can conclude that it is possible to use JSON with ROS within an embedded platform. We also can conclude that BDI agent simplifies the development of complex behaviors. This is supported by the metrics that we collected, such as the size of the programs, their number of lines, their number of words, and the need to use multithreading and locks. A disadvantage of the proposed approach is that it uses more computational resources. As future works, we should allow the use of action libs for performing actions. We also should port the proposed architecture to ROS2. And in the future, I will present this work as part of my master thesis, which also includes the combination of Jason-ROS with an active perception mechanism integrated within BDI agent's reasoning cycle. I would like to thank everyone for taking the time to watch this presentation, and if you have any questions, you can address them to this email. Thank you.